So we learn about linearization first, and then we'll show how linearization can be used to control system. So here we are going beyond ME312. ME312 is about x dot equals ax plus bu. You can write it in the as a transfer function and then use it, but you, x dot equals ax plus bu is not true for most systems. So this is it is beyond that, and this is actually going to help you to apply linear control to a nonlinear systems, linearization. Okay, so what I said was pole placement and LQR only works for a linear system of the form x dot ax equals ax plus bu. But most systems are nonlinear. So I'll write a general nonlinear equation. X dot equals f of x comma u. Okay. Here f is nonlinear. Nonlinearity could manifest as because maybe x has squared terminates, maybe there's x times u, and so on. Okay, so what we'll do here is this. We will linearize the system. So what does that mean? Which basically, this method basically will take this equation and convert this to something like this. X dot equals ax plus bu. This is okay. So that's basically the hard work you need to do to get that equation of that form. And once you get in that form, now it opens up pole placement LQR for you. Okay, so this is a very, very common approach to control system. You take a nonlinear system, linearize it, apply it. There are some catches to this. This linearization is only true in a small neighborhood of the whatever that operating point is. And so if in order to do this for something which is going to vary over time, like a trajectory, you need to do the linearization every single time. And that's basically the issue, but that can be actually automated. So let's see how to linearize the system. I'm going to use the Taylor series to do that. So I'll derive a formula, and then I'll show you the application of the formula. So linearization using the Taylor series. Okay, so we'll assume that x0, u0 is the operating point. Usually it's some kind of equilibrium position. So for example, for a double pendulum, it could be the vertically upward position. That would be the operating point. Now we'll replace, and let's assume that the system dynamics is f of x comma u. Okay, if that is true, then right, this should be true, because after all, x0 and u0 is satisfying the equations because that's an operating point. So this is true. Okay, so now let's do this. Let's take x and replace it with x0 plus delta x. So we take the operating point and we perturb the operating point, about the operating point, u0 plus delta u. Now let's put it in the Taylor series. So x plus delta x derivative. So this is basically comes from here. f of x plus delta x u plus delta u. Now, you might have seen Taylor series before, but we only have done that. You might have done this in one dimension, but really it's very, very versatile. You could do it in any dimension. So here it's two variables, x and u. So the way you do this is this should be x0, x0, u0. Okay, now this is x0 dot plus delta x dot equals. So this is where we'll use the Taylor series. So what you do is you write x0 u0 plus the partial derivative of df dx x minus x0 plus df du u minus u0 plus there will be, if you want, we can go further. It's 1 upon 2 factor d square f dx square x minus x0 square plus half d square f du square u minus and there's another term which is the cross coupling dx du, but essentially a lot of terms. These terms, what we'll do is we'll sub this as delta x, sub this as delta u. You see, this is delta x, delta u. And you can actually write here high order. So when I say high order terms, it's basically high order terms in delta x and delta u, delta x. Yes, so I'll write this down as one more time, x0 u0 plus df dx delta x plus df du delta u plus, people usually write it as hot terms, HOT is high order terms. Okay, so since delta x, delta u is small, okay, it's because you're doing small increments about the operating point, you can actually say that these hot terms are zero because of this reason, because they are small. Yes, so I'll rewrite this equation down. So let me write this down again without the hot terms. And one thing you want to remember is this df dx. When I do that, it's actually at x0 u0. So remember, that's just a function that's just taking the derivative of f, but you need to, it's basically a numerical value because you need to put this. Okay, now here's the thing we can do, which is we notice this fact. See this? This is true. I will call this, let's just call this 1. So x dot equals f of x0 u0. So if you go here, x dot equals this. So what I can do is I can just cancel these off. Okay, and so I'm left with delta x dot equals df dx x0 u0 delta x plus df du x0 u0 delta u. And now is the time when I actually get the linearization. So let's say that delta x, that small change, is actually capital X. Okay, this delta u is a new u. Then has to be that df dx x0 u0 is a, and then df du at x0 u0 is b. And so we have x dot equals ax plus bu. So this is x, this is a, this is b, this is capital X, this is u. Okay, so remember, to make it linear, all you have to do is just this. This is the linearization that we were after. Okay, so once you get F, which is the system dynamics, that's the equations of whatever motion in this case, you take the first derivative of F with respect to X and U. We've learned how to do that. That is basically the Jacobian of F with respect to X with respect to U. We know how to do that. Once we get that, that's A and B. That goes into X dot equals AX plus BU. You can use pole placement, LQR, get your K matrix. And then finally, the final step is, of course, you did implement this. So you say that delta U, or we said U equals minus Kx, but that is simply du is minus K times delta X. So this will be our feedback controller. Now, one thing to remember, and this is a common mistake, this delta U is basically that differential. It is not the entire control. So the control U has to be U0 plus delta U. So there is a nominal control, and then there is that part, which is the linear part. So when you apply the control, do not forget this. So this goes to the motors. Right? This is just a part of it, but this is the one which goes to motors. U0 is some nominal control. Usually U0 is the control which is required to keep the system steady in the absence of any disturbances. So, but many cases U0 is 0. For example, if you keep for the pendulum to be upright and when the mass of the pendulum is on the rod, the control U is just 0. Okay, so what I'll do is next, we have some theory here. I will show you how to apply this on one of the examples we've done before, the differential dynamic car. So let's apply this example. For the system where let me just not do this. Let me just write it as x dot y dot theta dot v cosine theta v sine theta omega for the system so and so, linearize it about an operating point x equals x0, y0, theta 0. That's the state. And then the control in this case is u v0 omega 0. Okay, so we need to linearize about x and u. So let's just call this, and if you want, you can call this x0, u0. Okay, so in this case, if you want to write it as x dot equals, you know what, let me write it as z dot. Let me just call this z, just because I think that it will be very confusing to see x as a vector state and x small x, lowercase x, also to be as part of v cosine theta. So here we can write this as x dot y dot theta dot equals v cosine theta v sine theta omega. So that is f. This is, you can see it is not a function, well, it's only state appearing here, but this is a nonlinear function. So first of all, the nonlinearity is due to cosine and sine, right? They shouldn't appear when it's linear. The other reason why it's nonlinear is because it's the product of control and cosine product of this. So second thing is reason is because we have v cosine and v sine. Okay, the third equation is actually linear. Okay, so how do we go about doing this? Well, we know that a, just write a new page. So a is df dx. In this case, let's call this, remember this is z, the definition. So we'll say that a is df dz about z0 u0, and b is df du at z0 u0. So we just have to evaluate these things, f zu. Okay, so let's do it one at a time. Let's compute a and let's compute b. Okay, so a is df dz, which is d dz of what, v cosine theta v sine theta omega. If you want, you can write this as, I mean, this might be a little better. Let's write it as d, that's the numerator, and the denominator x, y, z, sorry, x, y, theta. X, y, theta. Okay, so the way this is done is, if you remember the Jacobian, it's basically dv cosine theta dx. X of v cosine theta d dy v cosine theta d d theta cos v cosine theta. Okay, so we need to do the same thing for the second line, dx v sine theta d dy v sine theta d d theta of v sine theta. And then finally, d dx of omega d dy omega d d theta of omega. Okay, so we see some of these terms will be 0. Like here we have x and nothing here is x. So this should be 0. This should be 0. This should be 0. This should be 0. That's 0, 0, 0. So we left with essentially 0, 0. So derivative of v cosine with respect to theta is minus v sine theta. Then 0, 0. Derivative of v sine theta with respect to theta is v cosine theta. And then 0, 0, 0. Okay, and then remember this is linearization about x0, y0. So let's just put that value. So v0, v0, 0, 0, because it's linearization about that. Okay, so that's my A, which is df dz. Okay, let's compute B, df du. So the definition of B is it's df du. And what's du? It's basically v and omega, and then we write f as before, v cosine theta, v sine theta, omega. So again, we can distribute the partials like this. T dv, v cosine theta, t d omega, v cosine theta, d dv, v sine theta, t d omega, v sine theta, d dv omega, d d omega, d omega. Okay, so there's some terms which will go 0, like this one is 0. This one will be 0 because there's no omega in the numerator, same for this one. Okay, so we're only left with 3 terms which will be non-zero. So the first term is going to be the derivative of v cosine theta with respect to v is cosine theta, and then 0. Sine theta for the next one, 0, 0, and 1. So this is b df du, and then we want to put 0. Okay, so this is the answer, and then the other answer was here. So we got A and B, and that's basically defines our system. So to summarize, if you want to write it as so it'll be D Z dot equals the A matrix, which I wrote down earlier. It's zeros, 0, 0, 0, 0, 0 minus V0 cosine theta, 0, V0 sine theta 0, and 0. And of course, GZ plus cosine theta 0, 0, sine theta 0, 0, 0, 1, dw. Okay, so once you have this, then you can use it for feedback control.